So welcome back to the last session for today. Let me share the screen. One minute. Okay. So I hope my screen is visible to you and I am also audible. So in this session we'll focus more on the properties of this molecule, right? And what could be the end application of this kind of molecule, or let's say emerging applications. And again this session will be interactive because this is a tutorial session, so the number of questions will be higher. Remember, on 21st of November there will be a exam. The exam will be of multiple questions type. You will be shared with a Google form where you need to answer, and there will be a specified time will be given to you, but you can submit the answer only once, right? There is no dual submission, and once submitted the answers cannot be edited. Okay, so use these two tutorial sessions or few tutorial sessions to learn about the topic so that you know what is going on. Okay, in this session we'll discuss about stimuli responsive materials. So these are broadly materials which respond to external stimuli. These external stimuli can be physical, chemical, or conformational, right? Now my first question to you is, physical stimuli means, okay, I will not explain the physical, chemical and conformational, and why, and based on this external stimuli there will be changes in your molecule or the material. The material can change its property based on the external stimuli, right? Let me first briefly explain what is going on. So this molecule, if you focus here, this molecule is poly N isopropyl acrylamide. This molecule is thermoresponsive. If you take this polymer and make a solution, this is soluble at ambient temperature of around 20 degrees centigrade. But if you slowly increase the temperature at or above 32 degrees centigrade, this molecule will be insoluble in water and the solution will become opaque or non-transparent. This transition from a soluble hydrophilic state to an insoluble hydrophobic state is called lower critical solution temperature transition, right? This is LCST. The reverse is also true. There are some molecules which are insoluble in water at ambient condition, but at higher temperature they are soluble. Example is phenol. Phenol is basically carboxylic acid, which is sometimes used in domestic purposes also to drive away snakes. So phenol is insoluble in water at ambient condition, but if you increase the temperature to around 60 degrees centigrade, at or above 60 degrees centigrade, this molecule is soluble in water. So this 60 degrees centigrade is its upper critical solution temperature, or UCST. Okay. Then there are some molecules which are pH responsive. Like NH2 is pH responsive. If you have any amine functionality, primary amine functionality, then let's say around pH 2, this amine is protonated, so it exists as NH3 plus, and at higher pH this exists at NH2. So this is pH responsive. Now there are some molecules which are salt responsive also, right? Where this molecule can respond to changes in salt concentration also. So stimuli responsive polymers are classified into three parts. One is single stimuli responsive, second one is double stimuli responsive, third one is multi stimuli responsive. Now my first question to you is the following. So arrange these three molecules. Let's consider this as A, this as B, this as C. So if you are given an option to choose either one out of these three for your desired end application, which one will you choose? Or if I rephrase, which of this ABC is a preferred polymer for their application, right? You need to write the order. ABC, CBA, BAC, whatever, right? Now you have 2 minutes to answer it in the chat option. Write which one is preferred for their end application. Okay, so there are some answers. Let have the complete answer and then I will discuss. You can write the order or you can choose the most preferred option. Both are fine. Preferably, you should type the order. Okay, so I have some orders and we'll go ahead. Okay, one by one. So, Narendra Sahu, please unmute yourself. So, you chose option A.
Yes, sir.
Can you please explain why you think that this will be the best one? Yes.
Sorry, very effective.
Narendra, 1 minute. So, if you can please speak little louder, the voice is not coming through.
Single layer will be more effective than multi-layer, I think.
Why?
Very, these multi-layers are inside, and first layer is mainly we are working on the first layer, so single layer is very efficient if you're applying it on the end.
Okay, I'll come back to your answer. Let me ask other people also. Then I will come back to your answer. Naftej, Naftej, you wrote two answers basically. Please unmute yourself.
Yes, yes, sir.
You wrote two answers. Which one should I take?
I wrote two answers. In 1 second.
Huh?
I have given only one.
No, there are two answers. One at 1755, one at 17656. One is CBA and one is only A.
No, A I haven't given. CBA. CBA is
Oh,
correct.
sorry, A is not in the. Sorry, my mistake. Okay, can you please explain the order? Why you think that C is most preferred?
So C, as we can see, multi-stimuli responsive. More than one type of stimuli can be. It is responsive to more than one stimuli. So we can precisely tune any of the material according to the place of application of that final product, with according to one or more type of stimuli. Like if we need to use that polymer at high temperature, and also that should be water insoluble, and also according to the pH uses, so the polymer material should be responsive to more than one stimuli. If we use A or B type of thing, then it could either be temperature stimulus or water insoluble, but we can't achieve other properties also. For better polymer products, we should have multi-stimuli responsive polymers, I guess.
Okay, so I'm happy to say your answer is perfect. You explained all the bases. Thank you. So I can move on. So it is CBA as Naftej explained very nicely. So now we'll discuss about the singly stimuli responsive polymers, few examples, and then I will ask how these are responsive to this kind of properties, right? So first example is this one, temperature responsive polymer. I will give you the background and then I will ask you the question. So generally a temperature responsive polymer which is demonstrating lower critical solution temperature, it is soluble at a certain temperature, and that then at higher temperature it becomes insoluble, right? So whenever a molecule is soluble, it generally forms soluble in water, it generally forms hydrogen bonds with water, and then it becomes insoluble at higher temperature. Now my question is, why, let's say this molecule nipam, why this p-nipam, this molecule is insoluble at higher temperature? Can you write it in the answer? Why this molecule is insoluble at higher temperature? That is the question. Please type your answer, I will discuss. I will repeat the question. My question is, why p-nipam is insoluble at higher temperature? It was soluble at lower temperature, But when we increase the temperature, this molecule becomes insoluble. What is the reason for that? Okay. I give you 2 minutes to think and then I will ask few people to answer. Or you can type your answer, whichever is preferred. Okay, so few more seconds and then I will ask the question one by one. Okay, so we have some answers. uh, okay, okay. Navtej, please unmute.
Yes, sir.
Your answer is correct. Can you please elaborate little bit for the class?
Sir, when temperature will be increased, obvious that hydrogen bonding of the water molecules with the polymer of this type will be lesser. And due to this, that alkyl part, which are thought to be hydrophobic, will be oriented randomly in the solvent, and due to which the hydrophobicity will prevail, I guess.
Yes, you are very close. So, is there any weak interaction which prevails at higher temperature, which is leading to this insolubility? Can you think of that, Navtej?
Mm, no, sir. Right now, I am not getting the point.
Okay, fine. Let me ask someone else. Narendra is typing. I will wait for his. But your answer is perfect. Actually, near perfect. Only small thing is missing. I will explain. Let me wait for the Narendra's answer. Then I will explain. Okay, so Narendra, if you can unmute yourself.
Yes, sir.
Yeah, can you please elaborate?
As that you say, sir, people weak linkage है जो मुझे याद है कि printer was.
Okay, fine, good enough.
Sir,
So what
sir, can I
happens?
ask you one question also?
Yes, please.
सर जैसे कि आपने अभी बोला कि हायर टेम्परेचर पे इसकी सॉल्युबिलिटी कम हो जा रही है
Yes.
तो ये सिमिलरली कभी कभी ऐसा भी होता है कि हायर सॉल्यू मतलब टेम्परेचर बढ़ने से सॉल्युबिलिटी बढ़ जाती है तो उसका रीजन क्या होगा
Okay. Okay, I will explain. This is a good enough question. Fine. Okay, so I will explain both part. So for this particular
Yes, sir.
molecule at higher temperature, the van der Waals interaction between the alkyl moieties will increase and they overcomes or they supersedes the hydrogen bonding interaction. That's why this molecule becomes insoluble. This molecule becomes insoluble. So for the reverse question which Narendra has asked, I explained considering phenol as an example. So initially phenol molecule is insoluble in water. Why? Because phenol moieties have aromatic rings and these aromatic rings have pi-pi interactions. So these pi-pi interactions prevail and these pi-pi interactions predominates over the hydrogen bonding interaction which OH groups can have. At higher temperature, these pi-pi interactions broke down because molecule gets more energy to randomly orient themselves. So this order is missing. For pi-pi interactions to have, you need a specific order. The aromatic ring should come on top of one another or bottom of one another, otherwise this interaction will not happen. So for those kind of molecule which exhibits UCST, initially intermolecular interactions predominates and after that the interaction with solvent predominates. That's why they become soluble after some time. So Narendra, did I answer your question? Is it clear now?
yes sir but if someone is asking अगर हमसे कोई बोले कि सर वो एरोमेटिक नहीं है तो देन वी कैन तो हम उसको कैसे रिडिफाइन करते हैं?
Agreed. So agreed. So there will be something for a molecule to exhibit UCST. There should be some interaction between similar kinds of molecule, which predominates at low temperature over the interaction with the water molecule or the solvent molecule, right? So if pi pi interaction is absent, there will be something else, some other interaction which will predominate. Okay, I will take the question from Navtej. Please unmute yourself.
Sir, here we are talking about polymers like in PN,
Huh.
and we are comparing it with the phenol. That phenol is more soluble at high temperature, etc. How can we compare? Is phenol a polymer?
Great. Okay. So let me cite an example. Let me write something. So let's consider to look at the page. Let's consider this is your molecule. This is your polymer. Right. Phenol was a example basically. So let's consider this is your phenol, and let's make a polymer out of it. This is 4-hydroxystyrene. Right. This is a polymer. This polymer so exhibits UCST. At ambient temperature, this polymer is insoluble in water. When you increase the temperature to around 60 to 63 degree, this polymer becomes soluble in water because hydrogen bonding interactions supersedes over the pi-pi stacking interaction between multiple aromatic rings of the pendant moiety. This part is the pendant moiety, and there are other chains that also has a pendant moiety. Just for simplicity, I took an example of phenol, but basically we are talking about the polymers. Is it clear now, Navtej?
Yes, sir, this is clear. Sir, I have one more doubt that
Sure.
we explained on the basis that uh, at high temperature some polymers get soluble or some don't get soluble, and we deliver the fact that the van der Waals forces supersede the hydrogen bonding or they prevail behind them. But how we practically see them, these type of things? Uh, is there any practical proof to verify that the hydrogen bonding is stronger than van der Waals interaction or it is reverse at any temperature?
Okay, so this is a good question. Right. So, okay. So, what can be done is instead of PNIPAM, if you take a polymer which has amino acid backbones, in that case, the hydrogen bonding interactions can be observed using a technique called circular dichroism or CD spectroscopy. There, if you do a kinetic study, if you slowly increase the temperature and monitor the CD spectra of that molecule, you will slowly see the this CD spectra patterns is changing, and the characteristic peak will slowly disappear. So they basically do a kinetic study, and from there they can extrapolate and measure it. So there are basically a calibration curve where you take known concentration of this molecule and make a calibration curve, and from there you can determine the exact strength of the hydrogen bonding.
Fine, sir.
If,
Thank you.
if you want to know more, I can send you the relevant reference also. But that's a very good question. Thank you for that.
Yes, sir. Please do send the relevant reference for dichroism, circular
Okay.
dichroism, because
Sure,
we
sure,
also require this in stereochemistry.
sure. Okay, thank you. So I'll move on. So next example for us is just a minute. Just give me a minute to erase this part. So next example for us is light responsive moiety. So I will first give you the background, then there will be a question. So I will assume that all of you know geometrical isomerism or cis trans isomerism, right? Can you write yes or no in the chat? If you know geometrical isomerism or cis trans isomerism, write Y. And if you don't know, you write N, because without that I cannot explain this phenomenon. I'll just wait for a minute. Quickly write Y or N. If you know geometrical isomerism, write Y. Otherwise, write N. Quickly.
एमएससी फर्स्ट ईयर
Okay, so I have seen the answer and there is one no. So I will explain what is geometrical isomerism, right? So geometrical isomerism or cis trans isomerism, if you consider this molecule, 1 minute. So, Narendra, I request you to read about geometrical isomerism after this class because for tomorrow's class also we will need that concept. So, this molecule is a trans form of adjuvant, right? It requires more space, and then there is a cis form of adjuvant which requires less space. Trans form the both the aromatic rings after this functionality is on the opposite side. That's why it is trans. In the cis form, they are on the same side. In case of light responsive moiety, what is being said is the following, that light, if you shine light on this molecule on a polymer which contains this adjuvant moiety, based on the light wavelength of the light, this molecule can exist in its trans form or in its cis form, and based on that you can have a property. Right, so that is light responsivity. Now, if you want to have a light responsive moiety, there are two options. One is a molecule can be UV light sensitive. Second one is visible light sensitive. So here comes the next question. So let's consider UV light sensitive molecule as option A and visible light sensitive molecule as option B. So my question is, which one is preferred for end application? Option A or option B? Just write A or B in the answer column so that I can see. But write quickly so that I can move quickly. The question was, among UV light or visible light, which one is preferred? Write A or B in the answer quickly. In 1 minute, we will close it. Okay, so I have seen the options, and then most of you have chose. Oh, someone has chose A also. Okay, okay. Let me ask from the bottom. Sandipan, if you can unmute yourself.
Yes, sir.
Yes. So why it is B? What is your explanation?
Sir, in visible sensitive, we can show the color of the molecules.
Okay. Let me ask Aditi, if you can unmute yourself.
Sir, I have given answer that UV sensitive is uh, more preferred because the visible light is everywhere. So, which is visible sensitive, it can react very easily. But which is UV sensitive, it will not react easily.
Okay. Let me go to Navtej. Navtej, please unmute yourself.
Yes, sir.
So why
Sir,
it is
my
B?
explanation is this, that UV having lesser wavelength, higher energy. So
Hmm.
there might be some chances that it would damage the polymer or any of the bond because glycols And second is that even the natural light has more content of visible light and lesser content of UV light, and even then that UV light ruptures the DNA of our skin. So that is why, and if the visible light is everywhere, so we should be using that light to check the sensitivity of the material which we are using to form any type of polymer, not to the light which is in minimum quantity.
Okay, so Navtej, your answer is correct. I will explain to others why B is the preferred option. Okay, so whenever we go in the sun, in the open sun, nowadays what we do? We use sunscreen, right? At least some of us, the cricketers, Hardik Pandey, if you have seen him, he put lot of layers of zinc oxide because these UV rays can lead to skin cancer, right? So UV rays are harmful for your skin, for your eyes. That's why we put UV protected lenses also, right? So UV light is not preferred. I understand answer from Aditi. UV light can be specific, but uh, if you can perform the same work using a visual light, it is always preferred. And remember one thing: if you consider the visible light, sunlight as a visible light, sunlight contains around 5 to 10% of UV light because ozone layer has been depleted, right? So in summary, the answer is visible light because it is less harmful to the living cell, living body, or living organism, so that your end material can be used in those purposes. Okay, so we'll go ahead from this slowly. Okay, so this part is interesting. I will explain only with one option because that is easy. So okay, so I think all of you have read about amino acid. There are two amino acids, one is cysteine and one is cysteine. One having SH bond, second one is having S hyphen S or disulfide bond, right? So this exchange between thiol to disulfide is very dynamic. Even if you don't do anything, they will exchange very rapidly. And this is redox responsive transition, and they are used. That's why they are used for multiple application. At this point, my question to you is: what is vulcanization of rubber? Right? Think and try to write one line answer. What is vulcanization of rubber? That has direct correlation with this thiol. I'll wait for 2 minutes. I need one line answer, not a big essay. Write it, then we'll discuss. Okay, so let me see the answers. First one is okay. Uh, okay, I will ask one by one. I will ask first Aditi. Aditi, please unmute yourself.
Yes, sir.
Yeah, can you please elaborate your answer?
Sir, I don't know much about it, but there is some sulfur-sulfur bonding, and because of that, it becomes more stronger, and the elasticity is enhanced because of
What
the
about the
vulcanization.
brittleness?
Sir, it will be less brittle.
It will be less brittle. Okay, your answer is correct, but the background is missing. Okay, fine. Naftej, if you can unmute yourself.
Sir, like natural rubber is the polymer of isoprene, I guess, polyisoprene. So the polyisoprene is a linear type of chain. So layers of the polyisoprene can slip over one another. So we use SS bond. This is called vulcanization of rubber, due to which the bonds between the two adjacent layers of the polyisoprene are formed, due to which the slipping down of the layers is reduced, and we can say the brittleness will also decrease. And I can't comment on elasticity on the basis of this.
Okay, so that is almost a near precise answer. Fine. So both of your answers are correct. Okay, so there is another answer. Okay, that answer is also correct from Sandipan. So vulcanization is type of a cross-linking because it generates disulfide bond into the network, and this vulcanization increase the mechanical robustness and sometimes elasticity, because you need to take a comparison. If you take a comparison of a tire of a cycle and the tire of a scooter or bike, when it is totally inflated, the tire of a bike or scooter will look like a steel tire. It is so tight, but the cycle tire will not look right, because the cycle tire is little bit more elastic. So we can say that this vulcanization process increases the mechanical robustness of the rubber, and that's why it is used. So all the three answers are okay. So we'll go ahead. There are other few other examples using nitroxide and ferrocene, so I will skip that, so that for now, because so that the things are little easier. So the easiest, or okay, there is a hand. Wait 1 minute. Oh, where is the hand? Naftej. Yes, Naftej, please.
So what is mechanical robustness? And if we are increasing the sulfur-sulfur bonds, vulcanization of a rubber, how can it be more elastic if we consider that the natural rubber is more soft, I guess? And if we are doing vulcanization, we are making it harder. And how can we correlate it with the elasticity of the rubber then?
Okay, so this is a very good question. So it will take me few minutes to answer, but I will try. See, natural rubber is white in color. This rubber is sometimes it is used to make tires of kids bicycle, and sometimes it is used in raw state to make some cricket balls also. We used to call it rubber deuce ball. After few hits it will get cracked because it is brittle, because natural rubber doesn't have the binding forces in between, right? You can say it is a lump. So you basically, if you take some mud and just lump it together, there is a binder inside. When you add some vulcanization or using thiol, so you increase the interlinkedness of this natural rubber, which is basically a polymer, right? You increase the entanglement rates. Mechanical robustness relates to its mechanical toughness or mechanical property, which is measured by ultimate tensile testing strength, or ultimate tensile testing machine. What you do, you prepare a dog bone kind of a sample, you pull it from the both side and decide how much load your sample can take. If your sample can take more load, it is mechanically more tough or more robust. Now, I completely agree with Naftej that there is no direct correlation between mechanical robustness and elasticity. But if you consider that example, the elasticity of a iron rod is higher than elasticity of a natural rubber, because the iron rod can come back to its shape after it is straightened, but the natural rubber may not come back to its shape. It may break after some load. So the threshold at which your material will break, that is called the breaking point. and at that breaking point ultimate tensile elongation or UTE is measured. For natural rubber the UTE will be much less compared to a rubber which is vulcanized or an artificial rubber. Now is it clear, Navtej? If you have any further
Yes, sir.
query you can
Yes.
ask.
That is the hysteresis loop, I guess. That could explain it correctly.
Exactly.
Thank you,
Yes.
sir.
Okay. So we'll go ahead. Okay. So okay, coming to the pH response. Okay. So I request you to raise your hand. That's very easy to see rather than the chats, huh? As Naftaj is doing. So for pH responsive molecule for this session, we'll consider two very simple example. One is carboxylic acid. So carboxylic acid can remain in its two forms. One is carboxylic acid and second one is carboxylate. So carboxylate ion exists at higher pH and carboxylic acid form exists at lower pH. Things get interesting when you add a aromatic ring here. So when you add aromatic ring, what happens? Sometimes this molecule might be insoluble in water in its carboxylic acid form. If you add 2, then it is insoluble in water in its carboxylic acid form. But when you will take out this proton at higher pH, it might become soluble. So the solubility and insolubility of a molecule is is dependent on the pH of the media, and there are a lot of pH responsive material which is being used based on carboxylic acid. Just for a reference, I would like to mention that with increase in glucose concentration in the body, the pH can change, and based on that also you can make a pH responsive material. Now coming to tertiary amine can exist in its protonated or deprotonated form. At low pH, it exists as a protonated form. It becomes NR3H plus quaternary ammonium basically, and at higher pH, it becomes as a tertiary amine form only. Based on that, you can make molecules. Last example of this is chemoresponsive molecule. This will be little interesting, so please focus. I can repeat if there are any confusion. For today's session we'll consider this boric acid, right? And I encourage you to read from internet or from any other source about this. So boric acid molecule can form boronate ester. If you add one more OH here, so it forms boronate ester and that is stable. And this stability thing I think you are aware of it, because you know what is boron, what is diboron, what is boronate ester, all those things, all those transformation reactions you have read about, right? So based on this transition from boronic acid to boronate ester, this molecule can be glucose responsive because glucose has multiple uh, OH functionality. Glucose or any diol at higher pH can form bonds with boronic acid and it can respond to, right? So if you have higher concentration of a glucose in any media, boronic acid can form a bond and it can become a sensor. It can sense the glucose concentration of the media. Okay. Now if there are any confusion regarding this boronic acid part, please raise your hand. I will be very happy to repeat it because I want you to understand this concept. I will wait for 2 minutes if there are any query on this boronic acid part. Okay, there are two query. I will take Narendra's question first and then I will come to Navtej. Narendra, please unmute and ask your question. Okay, sir, explain it again. Okay, I will explain it and then I will take the remaining query from Navtej. Okay, so what I am trying to say is the following. Boronic acid at higher pH can exist as boronate ester. This is the phenomena. Based on this, what you can do, you can take a boronic acid like this. Let's consider this is a boronic acid, OH and OH. Now if you take a glucose molecule, glucose can have diol functionality or polyol functionality sometimes, like this. So at higher pH, this glucose can form boronate ester. At higher pH, this glucose can attack this one and form boronate ester, right? So in reverse, what you can think of, so glucose concentration in the media can be sensed by bordonic acid functionalized chemosensors, because at higher pH, at higher glucose concentration, the formation of this boron ester will be higher. And now if you can make this molecule this into a electrical sensor, electrical signal, then you can sense what is the glucose concentration in the media. Basically what people does is the following, I will explain. Please allow me few more minutes. What people does, they convert this, they attach a fluorophore tag into the glucose, right? Let's say they add fluorescein into the glucose, so now glucose molecule has become colored, right? So this color molecule, when it is bonded with this with this boric acid, the boric acid part will also be colored. So let's consider this boric acid molecule was a sphere, non-colored or colorless sphere at normal condition, or white sphere you can think. When you add this fluorescent functionalized glucose into it, it bonded with this and it becomes green, and this green you can measure using fluorescence microscopy. So in return what you are getting, depending on how much or how many green light emitting beads you generate, you can sense the concentration of the glucose in the solution. For this you need to make a conjugate of this glucose with a dye, fluorescein or other dyes. Okay, now I am happy to take any question if there is any. Please raise your hand. um, okay, Navtej, please unmute.
Excuse me, sir, like you explained that in the case of carboxylic acid, when the aromatic ring is attached, that is hydrophobic, fine. With increase in the pH, the solubility will increase. But what about that tertiary amine? Please repeat once. Because
Okay,
with
for
increase in
tertiary
the
amine
pH,
with decrease in
ammonium
solubility, solubility
cation.
is okay. Sorry. So with decrease in pH, more number of NR3 will get protonated and it will become more soluble. Let me explain it. Let me explain it in the slide. It will be easier. So let me add this one. Let me add a aromatic ring here. Right? Now this nitrogen lone pair can go into conjugation here. Right? So but if this is protonated, this becomes a polar site. So any polar site has higher capability of forming hydrogen bonds with water molecule. So at low pH, this molecule will form more hydrogen bonds with water and in turn make the molecule soluble in water.
So if we apply the same logic in the carboxylic acid case,
Hmm.
so carboxylate anion will also go in resonance stabilization in itself also. So with
Yes.
decrease in pH, there will be larger concentration of H positive ions. So by default, that should be more soluble now because the anions, that oxygen negative ion is, that is an anion, so it would show more solubility with water.
Okay, so let me explain. So, okay, so any carboxylic acid at low pH generally exists as its dimer majorly. When you go at high pH, it becomes carboxylate anion. So what you need to form a hydrogen bond? To form a hydrogen bond, you need a electropositive center and a electronegative center. Water molecule exists as hydroxium ion, right? H3O plus, and this molecule will exist as CO2 minus. So then it has higher probability to form hydrogen bonds with this H2 plus molecule. That's why it will become soluble at higher pH. And at higher pH, that's the explanation. Navtej, please.
Yeah, now it's fine that with hydronium
Okay.
ion it would form at higher pH where the H positive concentration is less. But if we also compare that at higher pH, H positive concentration is less. So okay, H positive cannot attack at carboxylate and make it carboxylic, but there would also be scarcity of H positive to form hydronium, the other part, to make it soluble now.
Yes, you are
Are you
correct,
get?
but there is a fine balance. So the solubility is, I will send you the relevant reference. So there is an interesting study which studied the solubility of benzene carboxylic acid at different pH to identify in the region of 7.5 to 8.25 this molecule is most soluble. At higher pH solubility decreases, at lower pH also solubility decreases. Based on your explanation, whatever you want to explain, that at very high pH H plus concentration is so less, there is no hydrogen bond formation forming sites. I agree with you.
Yeah, okay, sir. Thank you.
I'll send the reference. Okay, so Narendra, can you please unmute yourself?
Yes, sir.
Yeah, is your query answered or something remaining?
Yes, sir.
Is it answered? Have I
Sir.
answered
Yes,
your
sir. Yes.
query? Okay, okay, fine.
Yes, sir.
Thank you. Okay, thank you. So I'll go forward one or two more example. Let's consider the structure first. Right. So this is a very interesting molecule, PDMA. This molecule, where is the pen? This molecule has this amine which can get protonated at low pH. So this part is pH responsive. Interestingly, very interestingly, this molecule has this 2CH2, right? CH2 ethyl linkage, and this linkage can lead to van der Waals interaction. This is one of the unique cases where a single homopolymer is both pH and thermoresponsive. As few minutes back, Naftej explained that multi-stimular responsive polymers are better. It is even better if you have a single molecule which responds to two stimuli. It's like having an all-rounder in the Indian cricket team who can perform both the jobs instead of having two, right? So this is PDMA. The reference will be even better when I go for second example. I will come back to it again. So now you consider this molecule where to have, where is the pen? Okay, this molecule where this part is light responsive and this part is UV responsive, right? So both to have dual responsivity, here you have two different polymer chains. So you need to make a diblock copolymer, which is difficult to synthesize compared to a homopolymer. Now, if I go back to this slide, you will appreciate that the uniqueness of this DMAEMA, PDMAEMA, polydimethyl aminoethyl methacrylate, is a molecule which is easy to make and it offers you both thermoresponsivity and pH responsivity in a single molecule. If you want to directly compare, you can compare what happened after Hardik Pandya was injured. Consider PDMAM is not available, so you replace it with a molecule which respond to both two stimuli one by one. This will be more clear in the next example. This one. Okay. Now coming back to this one, I think during the class already I asked, are you aware of micelles and reverse micelles, right? So based on this understanding, I will try to explain what is going on here. My first question to all of you is, how many of you know what is an MP file? Right? Write yes or no in the chat so that I know where to start. What is an MP file? Write yes, Y or N in the chat. What is an amphiphile or what is an amphiphilic molecule? Okay. So amphiphilic molecules. So all the okay, we got a negative answer. Okay, fine. So I will explain. 1, 2, 3, 4. Okay, I will explain. Okay, so I will assume that all of you know what is a hydrophobic molecule and what is a hydrophilic molecule. Hydrophobic molecule are insoluble in water. Hydrophilic molecules are soluble in water. Amphiphilic molecules are a combination. They have both hydrophobic entity and a hydrophilic entity. I would appreciate if you still remember the answer Naftaj gave that time regarding double or multi-stimular response polymer. He answered the same thing. If you have both the options in a single molecule, we should always go for that. So if you have an amphiphilic molecule, if you have access to amphiphilic molecule, we should go for this, because based on the need we can use it as a hydrophobic molecule or hydrophilic molecule. Now, okay, now let's consider this part. Forget about these conditions and everything. Let's consider, for our understanding, these red parts are hydrophilic and blue parts are hydrophobic, right? So this is philic and this part is hydrophobic. So on the left hand side, what you are forming is a micelle with hydrophobic core, which can encapsulate any hydrophobic molecule. How these micelles are formed? So I encourage you to read about CMC little bit before the next class starts tomorrow. So how the micelles are formed? You increase the concentration of this molecule slowly in the solution, then at or above certain concentration they will form a 3D structure which is a micelle, and in this micelle you have a hydrophobic core inside, right? And this is, for our case, it's a reverse micelle where the outside is hydrophobic and inside is hydrophilic. Reverse micelles are generally formed in organic solvents and micelles are formed in aqueous solvents. We will consider one more example before we finish. So this is an example. Okay, again I encourage you to read about the geometrical isomerism, because I remember one of you are not aware of it. So you read about geometrical isomerism. This is a molecule where they used this azobenzene molecule to include the light responsivity, and this PDMA molecule where you can get both temperature and pH responsivity. So in turn you are getting a molecule which is both temperature, pH and light responsive. Triple stimuli responsive molecule, which is always better compared to a single or dual stimuli responsive molecule, because they give you more options. Few more examples. Okay, I want you to have a close look at this molecule for 30 seconds and then I will discuss. Okay, now the explanation. Now, okay, so now if you look at this closely, this is p-nipam, which is temperature responsive. This is tempo containing moiety, which is redox responsive, and this is this azobenzene moiety, which is light responsive. So this molecule, this is transform and this is cis form. This molecule undergoes transition from transform to cis form when you shine 365 nanometer light, which is UVA light, and when you shine 400 nanometer light or 400 or above, it transits from this cis form to transform again. So based on this molecule can behave as a multi-stimuli responsive molecule, right? So when we are using PDMA, we just needed 2 blocks, but in this case we need 3 blocks. So the last example for today is this one. Again you have a look, I will explain. Okay, now the explanation. So this molecule, this part is pH responsive, because if you have observed closely what is going on, this molecule is pH responsive, this part is temperature responsive, and this part I will not explain why it is environment responsive. You will get a text in WhatsApp with the image of this molecule, and I encourage you to come up with an answer why this part is environmental responsive. We will discuss it in tomorrow's class. Today I am not going to explain the environmental responsibility part. Anything else I can explain. Navtej, you can unmute.
Sir, just adjacent to the environmental responsive, we do have ethyl. So that would be temperature responsive too.
See, today I am not going to give the answer. You will receive a photo of this structure. I want you to spend some time on this molecule. Deliberately, I
Sir,
am
my
not going to
question,
answer this part. Your question
I
is
am
correct.
not having this question. I am having another question. If we compare
Huh.
ethyl and propyl, are they
Huh.
both temperature responsive or not? Or what is the comparison?
Okay. So ideally, if you have a propyl group that has higher possibility to give you temperature responsivity, but you also need to consider what else the molecule has. This part of the molecule has amide bonds, and amide bond leads to multiple hydrogen bonding sites compared to a normal NH or COOH. Due to that, even after having this propyl group, this molecule doesn't show temperature responsivity.
Why so, sir? If in the adjacents we have a lot of hydrogen bondings, then the temperature sensitivity decreases of any of the alkyl part.
Correct. Now we compare this structure with this structure. Do you see any difference?
Yeah, one is 2-degree secondary type thing and one is linear.
So that's why I'm deliberately not explaining this in full. I'll give you send you the you will receive the structure. You think about it. There are two
Okay, sir.
questions.
Okay.
First
Sure.
one is why this part is not temperature responsive and this part is temperature responsive, right? Although they look very close, and why this part is environment responsive, right? These are the two questions I will not answer deliberately. I want you to think about it, because if you don't have anything to think or ponder on, there is no fruitfulness of this tutorial, right? So I will end today's session here. I think there is a hand. Okay, it is your hand only. I will end today's session here. You will receive this image of the structure of this molecule in WhatsApp. Think about it, why this molecule is environmental, pH and temperature responsive, and why there is difference between responsivity between these two blocks, right? And I will come back tomorrow at 3:30 p.m. to take the next lecture and tutorials. And I thank you for attending this long session, and we will be closing. Thank you very much for attending. See you tomorrow. Bye.